house. We'll have to figure out a time.
Come
Mike
to
will be
Lily's
there.
grad party?
What's that?
Can you come to our grad party?
If I get an invite. I haven't got an invite
Well,
yet. What's that?
You gotta get wild if you come.
I'll get wild.
Is Tatum coming? Is she gonna be there?
Where? At my house or you go your grad party? I don't know. You got. If you send an invite, yeah, maybe. Yeah, no, she'll probably be at the house for sure.
But we have 5.
I don't know. She gets a little intimidated by a bunch of nerds. So. All right. Let's continue on. Finally, right? Homework is due today. Don't forget that as well. So what are we trying to do with this whole modeling thing when we're actually implementing in visual analysis? Right? We're approximating the response of a real world problem. That is the shittiest handwriting ever. Wow. Okay. What does our FEA model represent? An approximation of our mathematical model, right? We have this intermediate step that we take when we take a building, right, or a model from an architect, and then we want to model it in a finite element software program. We have to make some assumptions. We make a jump to this mathematical model. That's where we're making assumptions, like wild assumptions, which we'll talk about here in a second. Okay, so we need to take that real world, and we're going to make a mathematical model, right? We do that, and we want to capture the behavior of interest, right, to an acceptable level of accuracy, right? That's subjective, right? What's accurate enough without making the model too complicated. We obviously don't want to spend our lives on it. At some point in time, you guys will no longer be in academia, okay? Some of you will be coming up really soon, right? Some of you have made that transition where time is money, right? You can't spend all day creating a model of that cantilever for the homework, right? Okay, you gotta be efficient. All right. There's expectations though when you guys first get out there, right, that you guys don't know anything. Right? We all were there. I was there. Right? You don't know anything. There's a lot of patience involved.
So it's just the expectation to eventually get out of that.
Yes, eventually get out of that phase. Yep. Some of you will get out of it faster than others, James. All right. So with this, when we make that jump from the real world to the mathematical model, we make a lot of simplifications. We did it in our very first homework assignment with our concrete column, right? We made a lot of assumptions in our mathematical model. In this case, we might simplify loading, some examples of which would be, we talked about it on Wednesday, story shears for lateral loading, whether it's wind or earthquake, right? We can apply those in tons of different ways, right? We could apply it as a point load on the diaphragm, or pressure on a wall, line load on an edge of the diaphragm, line load on a column that then takes it to the diaphragm. And all of those simplifications come from going back and saying, I want to capture some behavior of interest. Am I designing the diaphragm? Am I designing a brace frame? Am I designing a column, right? Am I designing a gravity system, lateral system, right? Am I designing the foundations, right? All of those things. Some other simplifications we make with respect to loading is, do we want to consider self-weight? Self. Load magnitudes, right? With respect to load magnitudes, right? If our applied loads are so significant, right, then our self-weight might be a moot point, right? If we were looking at designing, say, the global diaphragm, or if we were designing a shear wall at some edge of the building, we might be able to just ignore some of the self-weights from all of the individual members, right? Earthquake loading, for instance, right? We're not going through and applying the earthquake load. That load's based on mass, right? Mass and acceleration. We're not doing that at every little member, right? Some of the advanced analysis methods like time history, if you guys were talking, in Mike's class, right? Modal analysis, time history analysis. You jump to another level where you have more weight, quote, I guess no pun intended, weight associated with the weight of our members in your analysis, right? They play a bigger role when you're looking at time history and you're actually shaking a structure with a real earthquake, right? So we can ignore self-weight sometimes. Yes, Aaron.
I was looking at this, I don't know why, but I was looking at jobs the other day. I was looking at this company.
Whoa, should I be talking to Tom?
No.
Okay.
And they were talking about how they do specialized anchorage for seismic, like anchorage for stone veneer or any sort
Yeah,
of
architectural
cladding.
components.
Yeah.
Yeah.
How, like they were saying they do like ton of testing and like really go in on the detailing on that.
Yep.
Is that typical, or do you have like kind of a typical seismic anchorage for a lot of different veneers?
I mean,
Like,
in
what
their case, it's probably a very proprietary system, right? So I
Yeah.
mean, like a solar wall that you see on the side of, well, Norm and the business building, it's basically just big black perforated wall panels and stuff like that,
Yeah.
right? The air travels through and the sun preheats it. It's an energy efficiency thing, right? So that's made by a specific manufacturer. They plug that as like, use our product. And as part of that, they do a bunch of testing to make sure that all of the system from the actual panel down to the connection to the structure is adequate for all of the required loadings.
But like just regular brick or panels or rock or anything that gets clad on there, I mean, is it typical to like run an analysis for every different kind that you do, or is it more typical to just kind of have?
When you do
generic-
brick veneer and stuff like that, that goes back to an architect usually specifies, other than like ledger angles to like hold the
Yeah,
brick
yeah.
up vertically.
Yeah, I'm
All-
just talking just to like stick it to the wall so that you get a
Yeah,
little bit transfer.
yeah, usually those are still proprietary clips, right?
Yeah.
And then you would go to that manufacturer and they would say, okay, here's a table, if you have a double white wall that's sitting on the outside, you're gonna need to use this clip at this spacing, right? Maybe 48 inches on center horizontally,
Yeah.
48 inches on vertically. And then, yeah, they do a bunch of testing, because you can get away from our analysis if you're able to put it in the lab and verify that it can handle it, right? There's some factors of safety go associated with
Yeah.
it, but then after that, they just get a report, like, if you guys seen like, the ESR reports, engineering service reports or something like that, where they go through and they like test Hilti anchors. When you go out and you put a metal deck down on a building, and then they can do powder actuated fasteners, they essentially take like a gun cartridge, like a 22 shell, and they use that to propel a steel nail that'll go through the flange of a steel beam, right, through the deck, and that's how they fasten it. Well, they go through and they actually do physical testing of it, and then you end up getting these big tables of allowable values. And
So you don't, as a structural engineer, often design that to that extent. It's more of like a specifying this hanger, and I know
Yep.
that the hanger's good for this value.
Yep, very similar, yep. And it, like, when you get to veneer and stuff, that's more of an architectural component.
Yeah.
And that lands
It
on the
just scared
architect.
me. They were like, "We do all this anchorage stuff," and I'm like, "Shit, I don't."
Well, I
I'm
mean,
pretty
so
comfortable
like,
when I do it.
yeah, I mean, some people like A&E Dynamics, they do
That's who it
all
was,
the
actually.
curtain walls, right?
Yeah.
And so they have found themselves in this niche market where there is a manufacturer and they're like, shit, we have to like give an allowable value for this.
Yeah.
And so they gotta go to an engineer. And so they end up, yeah, someone has to analyze it if they don't do testing.
Yeah.
Or they can, like in California, if you do testing, you have to have a structural engineer review that testing and sign off on it to make sure that it's adequate. So we simplify loading, we simplify materials, right? Linearity versus non-linearity. Homogeneous. Homogeneity versus anisotropic. What? Is that not good?
That's good.
Isotropic. Right. What's VA good for? What's RAM good for? RISA. Linear or non-linear? Linear, right? You can't do non-linear stuff. This is like bend over the stress strain curve, and now we're yielding. On top of that, maybe even when we start looking at strain hardening, right? That happens in steel. Remember from 315 pulling steel apart. Whether it's homogeneous, right? Anisotropic or isotropic, right? The material performs differently in two directions. Is it the same material throughout, right? Again, VA, it's got to be homogeneous. It's got to be isotropic, right? VA doesn't allow us to look at things that are not that way. I would recommend the help file. If you go in the VA help file, it'll say like about, or it'll say limitations, right? read those limitations. When you're in RAM or you're in RESA or you're in, what else? What was the other ones? Someone else was in, someone said ETABS, right? Like in all of those programs, you could go out to the help file and they will list out what are our limitations for this program. Okay, those are always critical to look at. Simplify materials. We also simplify shapes sometimes. And assemblies, right? A lot of times we might not design the concrete on metal deck. We can go to a table that designs it for us. Have you guys done that in masonry or metal deck, right? So a lot of times we'll just ignore that. We'll just put something in the model to hold its stiffness, but we're not actually going to design it, right? So we're simplifying it when we're actually modeling it. We can go back later and design it by hand in an easier way, which would be tables. We simplify stress behavior a lot of times. You guys remember from, well, some of you guys took some of the first concretes. I guess you took 315 and then 400 level concrete and 500 level concrete, right? Some of you guys have taken all of them. You've taken all of them. You've taken all of them. Taken all of them. Taken all of them, right? All you graduating, right?
Yeah.
So like looking at two-way action versus one-way action for concrete slabs, right? We make some pretty bold assumptions with respect to that, especially when we get close to that 2-to-1 ratio, right? Where we start changing that performance. If I was on a one-way slab, but I was still standing really close to the end of that one-way slab, right? The chances are it's going to act two-way, right? But we make the assumption it doesn't. So when we put in areas in our finite element analysis software, right? And we want it to just span one way or two way. The code allows us to make those simplifications, but does the real world really behave that way? No. There's a lot of indeterminacy in the real world. And so it might not span just one way or two way, right? There's a lot of complexities, but we make the simplification.
Would it be conservative to always assume a two-way slab?
No, because you might have more, one way assumes that the force only spans one direction, right? Two way, like especially when you're in like a box, if you looked at columns and columns, right? And your stress, the load is going to be spanning like this, right? That's going to do a lot different than if you said that this thing spanned one direction. Because now, right, now this member has this much tributary area versus now that much tributary area. And you got to think about how you're doing that also. I mean, the 2-to-1 ratio, right? Do you still assume the two-way action when you have a concrete on metal deck where the cross-section looks something like this? Whoa, 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 whoa. Right? And so you have a very specific strength direction. So even though the aspect ratio for this panel does this, but you're gonna land this deck so the flutes go like this, right? Do you still assume one way? Concrete says you might be able to assume two way, right? It's up to you. I'd assume one way.
Your deck doesn't span two-way.
But it's still like concrete slab in general, right? Stiffness wise, right? So I mean, there is probably a point where maybe you have.
Why wouldn't the load be attracted to the strong axis with the?
Oh, it totally is. But if you had, say you had some weird framing going on where you're like, right, you have, say, this is like a void space, but you decided to run the deck this way anyway, right?
Yeah.
This is still quite a bit stiffer, it's shorter. But just in terms of simplifying the erection of the building, you just said, all right, just lay the pan deck this way. Maybe they decide that later on they're going to put a stairwell in here. They're going to cut that out.
Okay.
In the meantime, does it span this way or does it span this way, right? And you gotta load that in VA. Do you see it, Madison? So like, if you had, this is grids, right? 4 columns, you got 4 beams, right? 1 in the middle, these are joists, and you decide that you're gonna lay this deck down so that these flutes span this direction, right? So then here, obviously, it makes the most sense, I'm gonna ruin this paper. It makes the most sense that that deck spans this way, load's gonna span this way. But if this was some part of a grander grid system, right, and we had a huge building, right, the chances that you want to tell the fabricator to change the direction of the deck, you might not want to, right, just for the efficiencies of laying this all out and connections of stuff. So maybe you just lay the deck out this way, so it continues to try and span that way, but in reality it's braced pretty short on the other direction, to where, well, this a lot of times can be 3 inches plus. Okay. So there's pretty good amount of stiffness headed in that direction. Maybe this starts spanning this way.
Would you have to support that anyways in some way? That span, obviously it's.
But it depends on which way you wanted to assume that it's, right, I mean, if you assume that it spanned this way, you'd have to design it that way, right? You'd have to look at the forces that that concrete would see, and you'd have to make sure that it can handle it going that way. You could go through a table value and say, okay, maybe this is 12 feet, right? And then this is 6 feet, right?
So the way it spans just determines where you sit the boat.
Yeah, I mean, which way you assume it spans, right? That's the assumption you get to make as a designer, right? And yeah, stiffness attracts load, so you might want to assume that it continues this way. You might, as a designer, say, I don't even want to deal with thinking about the possibility that that's an option, and I'm just going to tell them to change the deck direction and tell them to go this way. Right? I'm just saying there's tons of those little one-off scenarios that you as an engineer have to just thoughtfully think through of what, when I create my VA model, because I want to design these, say these beams, right? Or I'm going to look at what the pressure is on this deck. I need to be thoughtful as to, okay, well, what does this beam see? Is it going to take any of this load from here? Or is that load going to just travel to the end girder, right? So, all right. So one way or two way, we make a lot of assumptions for plane stress. Or we called membrane action, right? Obviously, if we're designing, say we had a cast-in-place concrete diaphragm, and we put it out on this plan view, right? We had this grid system, we have this concrete on there, and we were actually designing the diaphragm. We probably want to make sure that we don't assume that it's a membrane, right? But if we were designing, say, the brace frames, say there were 2 brace frames at the ends of this building, right? And now we're looking at this diaphragm, we're going to model this diaphragm, but our interest in this model is to design these brace frames. We might say, well, screw it, this diaphragm is really, in the eyes of the brace frames, only trying to transfer, say, this wind load that's acting on the edge of it, right? And if it's just trying to take this load and dump it into each one of these, then I am just going to assume this is a membrane, right? And if you had a large model, taking away all of those degrees of freedom, right? 3 degrees of freedom at each node of each plate element, right? It starts really reducing the amount of work, the analysis that the program has to do. And so it can simplify things and make things go faster, right? So-
Membrane means it doesn't have out of plane.
Out of plane, no out of plane stiffness. It works like a shell. So we make simplifications for stress. We make simplification for boundary or inter-element connectivity. Any ideas for some of them with respect to the foundations? What type of simplifications do we make?
Fixity.
Yeah, we sometimes we just pin it, right? Are we really pinned? No. Have you guys seen a train go by on the train tracks and the rails, how they move down and up, right? Dirt's a spring, right? not sitting on a perfect pin, right? It's not infinitely stiff. Buildings are the same way. So sometimes in foundations, we assume it's pinned even though it isn't. We assume it's fixed even though it isn't, right? Sometimes we do some level of soil interaction. And the code allows us to do that. Right, we start putting springs under our foundations. Those springs, right, the spring constant we use is based off of a geotech investigation. Right, another fellow civil engineer goes out there, kicks the dirt a few times, feels how, I just still like, it just blows my mind they get paid to do that shit.
It pisses me off.
Right?
They get like, it's like,
Oh.
they get like 10,000 bearing and then they're like, I'll give him 2.
Yeah,
I'll give him 2."
exactly. Just to make them feel
I
good.
hate it.
It's like, what the fuck? Anyway, so, yes, pin, fix, soil interaction, you get to,
And then we're the ones that get yelled at. Like,
Yes.
Big ass footing.
Totally.
Like, why do we need a 10-foot footing?
because you gave us 2,000 pounds per square foot. All right. What do we do? What do we do at beams to beams, right? We make some simplifications. We make them pinned connections if they're shear tabs, right? You guys gone through like partially restrained moment connections in steel yet?
I don't know that we're gonna get there.
Right? There's a whole like section about PR, partially restrained moment connections, right? Those would not be perfectly fixed, right? Fully restrained or the other ones, those are generally what we deal with. But in some cases, maybe you have a partially restrained, right? You would maybe want to make some simplifications for our boundary conditions, maybe put a torsional spring in there instead of actually fixing our members together. Because it's not gonna have its absolute stiffness. We make some other ones for what we're doing on our diaphragm. To our beams and our columns, right? We have this guy right here, right? This is our building. We have a diaphragm that sits here. We got a lateral load that's on it, right? How is this diaphragm interconnected to all of these beams, right? And we know that it's only connected at nodes. Exactly. I'm so proud. Nodes, right? And if there's no nodes on this beam, that diaphragm is not connected to this beam, right? And so when we're looking at this brace frame, we might want to split this member up into 100 smaller members so that we get a nice uniform connectivity of this diaphragm to this beam. Out here, right, this guy's resistance isn't going to do much, but there's some added stiffness of this beam. So maybe we split it up into 10 members, right? So we make some simplifications with respect to how these are actually attached. In the real world, we probably have a beam, trying to draw it on the board with this thing. Right, we probably have a beam that sits something like this. We might have a headed anchor stud that sits like that. Right, it's welded to the top of the beam here. So we have connectivity. Those studs are probably spaced anywhere from 6 inches to 2 feet on center. Okay, you might assume those are our nodes, right? There's connectivity. Some of these, like we're talking like 13,000 pounds or more that can be transferred through here, right? Or even more than that. So we make some assumptions onto how those are connected, all coming back to this idea of want to capture the behavior of interest to an acceptable level of accuracy without making the model too complicated, right? And this is where practice, right? Practice comes in too. We make a lot of simplifications that are common and that are used in a lot of analyses. We have these pinned, fixed foundations. That is so not the real world, right? But we make this assumption and it's done all the time. It's done all the time.
Even with some like really deeply drilled things, would you still not even assume like a fixed?
You can still assume a fixed.
I'm saying, would that be more accurate, like, if you do like some really deep drill?
I mean, it
figures?
depends on the stiffness of the soil itself, right? I mean, if you have like really deep, right, you might gain some stiffness, but if you're going really deep in, say, a clay, then you've got this big, tall
Still just
pile, and it, when it tries to deflect, it's got clay to resist it, right? And so it's still not going to be as stiff as maybe a 4 foot deep, like thick spread footing sitting in like a blasted out bedrock, like, you know, in like New York City. And they're super lucky because they have bedrock, and so like that's why they can put up massive buildings right next to each other. It's all rock. And no earthquakes, which is amazing too. Homogeneous materials, what's something that's not homogeneous that we design all the time? Wood. Concrete, right? So it's like we make this assumption that it has this nice, you know, modulus of elasticity throughout its entire length, right? It behaves homogeneous even though it does not. Concrete, right? We make some simplifications for it's going to crack. Well, that's going to change its section properties, right? But again, we assume that that section property is consistent throughout its whole length. Even though we might get a crack that's like once every 5 feet, I don't care. We're going to say that everywhere it just smooths out in the end, right? So it's a huge simplification.
How come we don't do any testing in timber design?
What do you mean testing?
Like, I want to see some beams being broken, so I can know what it looks like to be 5% overstressed or 10% overstressed or understressed. You know what I mean? Like, there's no grip to like what that actually does, especially when we have such a like non-homogeneous material that could have like twice the strength that it could have. You know?
Yeah, it would be cool to set up
like,
one.
bunch of different
Yep.
lambs or
Yeah, well, I mean,
different
you
grades of
honestly,
duck
you could
fur.
just go get like a 6x6,
Yeah,
right?
even
And
that.
just put it in bending.
It'd be
Here's
cool
the
to see
video.
what
That
it
would be,
actually
and like get
fails.
what you calculate as the capacity versus like putting, even like just putting the truck on it and seeing what.
Yeah.
Mike has that
That's a
video
good
of
point. I like
breaking
that idea.
Frozen glue.
Yeah, they have broken frozen glue lamps. Garrett did that as his professional paper.
I love that video. His head just pops into the window.
Yeah.
It's like,
So we make assumptions for pin-connected elements all the time. In reality, we know that that's not the case, right? We have bolts that, like shear tabs are a very common example of this pin-connected element that we assume. Not the case. Diaphragm stiffness, this is a big one. Not to put you on the spot, Aaron, but when you're in Hicks and you are calculating the loads, say this is a wood building,
there we go.
okay?
That's my jazz.
Very simple, very good for simple engineers. Okay. So we got this nice, beautiful wood building. We're gonna say all these are bearing walls. Redundancy all over the place. We put 10,000 nails in it. A lot of energy dissipation possibilities. So we got 2 bays. Maybe we have some interior walls, right? We have a uniform load. And you say you have a shear wall here, a shear wall here, and a shear wall here, right? 2 bays, 3 walls. What do you take as, say this is L and this is L, what do you take as the shear force on that?
Half of the total shear force of this tree, right?
This guy?
That's what I would say.
Depends on the stiffness of the diaphragm.
Okay. I do not like that assumption. That assumption happens all the time, okay? All the time. I do not like that assumption. That assumption assumes that you literally have a pin at the center, right? So this, you're saying this beam does this. And it does this. 2 simply supported beams sitting right next to each other gives you this, right?
Yeah.
Is this diaphragm that could be like 30 feet deep? Does it behave, is there a hinge? Do you think there's gonna be a big hinge here?
Depends on where their sheathing gap is. But I agree.
Sheathing gap, I mean, when you're doing your diaphragms, don't you tell them that they need to do something like this? They stagger it, gives you more shear value for the
Yeah.
diaphragms for you, those of you in wood.
We always assume like they orient them the worst way. And so I think the worst value is possible because you never
But you
know.
don't know, right?
Yeah.
So then you're assuming that you got this nice hinge here,
So you're
where
saying
you're
you
saying
run a
there's no wood members here or no wood members here, right? If you're pushing on it this way, you got this big tension force, this big compression force, right? This assumes a pure hinge, right? No rotational restraint or connectivity between each one of these diaphragms. Did you know if you looked at this as one solid beam, what that reaction will be? So you did 0.5, right, times 2L, or just essentially L,
Yeah.
WL. If you assume that it's a continuous beam that runs across this, which is the way I would typically do it. I like, especially if you have multiple spans, I just go in VA, you draw a member. All that member is just the same member across the entire thing. Maybe you've got like 7 or 8 of these bays, right? Based on that, you get 1.25 WL. You get 0.325.
With all the shear
No,
walls being the
3
same
seven.
stiffness, you're saying?
Doesn't matter.
It shouldn't matter, right? Like all those shear walls are the same stiffness?
Yeah, when you're assuming that they're restraining the diaphragm sufficiently, yeah. Because you start looking at that stiffness playing in, then it starts, this thing rotates. When it rotates, then there's torsional forces that you're gonna have to incorporate. And then you're starting getting into, okay, now these diaphragms, are they semi-rigid? Are they rigid, right? This is that scale. You can go from one end, which is assuming that it's simply supported, right? And it's just based on tributary area. Then you start thinking about stiffness and load path and continuity of the system. Then you're saying, okay, well, does it really behave like one continuous beam, right? Is this pretty much an integral beam over a bunch of supports? Do we assume those supports are stiff enough that they stay restrained? Or do we start looking at the fact that this thing starts moving, and when it starts moving, then we get
Well, it
torsion?
depends on, doesn't that depend on whether your diaphragm, you're gonna have to be pretty deep in order to be rigid enough to start displacing your shear walls like that, right? Otherwise, you just get,
Yes,
the
and-
load just gets attracted to the other shear
Yes.
wall. Because, the diaphragm just
Yep.
deflects.
And in ASCE 7, is it ASCE 7? Yes, ASCE 7, there's checks in which you can look at, okay, what's the displacement of my walls? What's the displacement of my diaphragm? And if my diaphragm displaces, I think it's either 2 or 3 times that of my walls, then I can assume that it's flexible, right? But when you say that it's flexible, you're gonna say that, okay, it is way more flexible than the supports. I'm gonna assume the supports are fixed. And if the supports are fixed, then how do I assume that my diaphragm deflects?
So how are you getting that 1.25 WL?
That would be a
What's the
continuous beam over 2 supports, pinned.
Or you got like a negative moment practically, but obviously not.
Is that like 0.6 of one?
I think it's 1.25.
difference? Wait, with two
Well, no,
supports,
yeah, but that's
so
divided
no
by 2,
support
yeah,
in
it's
the middle, or what?
0.625.
What's that?
I'm still confused about how you modeled it, like.
I put it in VA.
You're saying that it's like a continuous beam versus 2 simply supported beams, and so it attracts more load because there's moment transfer
As in
through the
no
beam
hinge
over the
there.
hinge.
There's no hinge there,
Yeah.
right? There's the model where this is simply supported, 2 simply supported beams, basically 2 bays of diaphragm.
Yeah.
That would assume that there's no connectivity. We've got a big hinge here. If you assume that there's enough connectivity there, right, you might suck more load to that center. Okay. On the inverse of this, though, right? Now you can design the walls on the outside for 0.75
Which sucks
WL.
sometimes because often your exterior walls are the best shear walls you have, and the interior, if you do add another one in the middle for aspect ratio or
Yeah.
something.
And so then if you do, so then that also assumes a pure connectivity across there, right? It's saying that it's not gonna crack, the stiffness is gonna stay the same. If it does, it's wood, it's probably gonna crack, it's probably gonna displace a little bit. If the minute it displaces some, this is gonna go up, right? So I might argue you might design some of these interior ones for this value and the exterior ones for the 0.5.
I always wonder too, like when you add gypcrete on top, that adds stiffness. I mean,
For
there's
sure.
the more it's, like you
Yep.
pile on that stuff, like it
For
adds
sure.
a lot more. than what's good. It's also like with wood, there's so many different ways to frame it. You're just kind of like guessing how they're gonna actually do
Yeah,
it.
for sure. I mean, that's why we get paid the big bucks, right? Paid the big money to do this, right? So it's interesting, right? Those are huge simplifications that we can make with respect to modeling or taking the real world and making simplifications out of it, right? Especially when it comes to diaphragm stiffness. So we make those assumptions all the time, right? Not that they're right or wrong. That happens all the time. I've done it where I've done just tributary area. A lot of times though, by the end, I started doing this a lot. where you just modeled it as a
That's
continuous
smart.
member. Right? And it's really easy to do. You just put a continuous member. It doesn't matter how big it is. It just matters the fact that it's all one stiffness, right? And you put a uniform load on it, and you look at the reactions in VA, and boom, you've got what your shear should be at each of your walls. Right? All right. So we use this mathematical model as our framework for development of our finite element model, right? And based on that mathematical model, all those simplifications here, then we need to then start checking out what type of elements need to match element with desired output or intent. Right? In this case, it'd be like, do we use a plate versus an area? Right? Do we care about stiffness? If we care about stiffness of that element, maybe we want to use a plate. Right? If we're just trying to push our load across our model and just try and load elements, maybe we ignore the diaphragm altogether. Right? We're talking about this again. And we make those assumptions using an area. Maybe we just use an area, not a plate. Right? Plate versus a beam, right? Do we put a plate on this whole thing, right? Or do we come back and just say, fuck it, I'm going to model this diaphragm as a beam, right? And then I'm going to figure out what my distribution of load is. But then I can design my shear walls for, or brace frames, or moment frames, or whatever they are, right? You got to make that decision. Do we assume membrane type of element versus a bending type of element, right? If I'm doing a time history analysis on Norm Asbjornsen Hall, right, I'm going to hit it with an earthquake. The out-of-plane bending of the diaphragm probably adds quite a bit of stiffness in some aspects of that building's performance and behavior that I would want to capture if I was shaking it with El Centro, right? If I was shaking it with the Hebgen Lake, right? Earthquake.
Did I do that? Did I get an earthquake?
I don't know if that's one. That's actually. I'm sure it's recorded. I'm sure you can hit it and do it. They record it on a seismograph somewhere.
There's
That's
a
the one that-
seismograph under.
Oh,
There's a seismograph under Roberts Hall. Yeah. What's that?
That's the one that caused.
The landslide. Yeah. The epicenter wasn't there. It was. I can't remember where it was.
Island Park.
It may have been. Yeah. It may have been. There's another big one in Helena.
That shaped the city, yeah.
Yep. Stuff like that. So anyway, so membrane versus bending are things we need to look at. Okay. As we take that mathematical model and we put it into the finite element model. The next one is discretizing, right? Now that we've selected these elements that we're going to use based on how we think this thing's going to perform, how, like, or I guess not how, but what type of results we want out of it, right? Now we then discretize, and as we have talked already, this is a big deal. Right? This is a big deal. How is it almost 9:50? Aaron.
I could just start watching recorded lectures if you want to get
Right? So when we discretize, if we look at beams and columns in a structural model, we're really trying to, or we need to, capture connectivity and compatibility i.e. provide adequate load path, right? We need to provide adequate load path. So when we're picking beams and columns, right, and we're discretizing them, deciding where they start and stop each of our individual elements, we're doing that in an effort to capture connectivity and compatibility, right? Obviously, this joist is connected, oh shit, we wrote all of this stuff, didn't we? Right, so we got, in here, we're gonna have, right, joists framing into column, or into girders that then frame into columns, right? We need to select those and connect those as such to make sure we capture the connectivity and compatibility, right? So if these are shear tabs, we're gonna wanna go through and release the moments, right? It's gonna be a pin, so we're gonna wanna make sure that we're capturing the connectivity of those members. Typically, I say typical, I guess, applications. Only require one element per mathematical model member. Right? You've seen VA models now. You modeled the homework by now, most of you, right? Just one element suffices as gaining, right, the connectivity and compatibility of that element, right? We only care about what's going on the outsides, right? Sometimes though, we might want to split this element. And there's a couple reasons why we can talk about it Monday.
Service level.
Oh, this is funny.
I took that as.
Well, I was there Monday, but.